two swimmers plan to cross a river with a current speed of 2.0 kilometers per hour. Swimmer 1 aims upstream so that the resultant gives a straight path to the middle of the river, swimming at 2.5 kilometers per hour relative to the water. Swimmer 2 swims perpendicular to the riverbank, also at 2.5 kilometers per hour relative to the water, reaches the middle of the river downstream, and then walks back upstream along the bank to the middle. At what walking speed should swimmer 2 walk in order to arrive at the middle of the river at the same time as swimmer 1? Let's visualize this problem. Here we have a river with a current flowing from left to right at a speed of 2.0 kilometers per hour. We'll represent the river banks as horizontal lines. The width of the river from one bank to the other is 2h, where h is the half width of the river. The goal for both swimmers is to reach the midpoint, marked as point M here. Let's first understand how swimmer 1 crosses the river. Swimmer 1 starts at point A on the bottom bank and aims to swim straight to point M in the middle of the river. Since the swimmer moves at 2.5 kilometers per hour relative to the water, but the water current is 2.0 kilometers per hour, the swimmer must aim upstream to counteract the current. The resultant velocity will be directed straight from point A to point M. Let's calculate how long it takes for swimmer 1 to reach the middle of the river. We need to find the perpendicular component of the swimmer's velocity. Using the Pythagorean theorem, we can calculate this as the square root of v prime squared minus v0 squared, which is the square root of 2.5 squared minus 2.0 squared, giving us 1.5 kilometers per hour perpendicular to the riverbank. So the time it takes swimmer 1 to cross is t1 equals h divided by the perpendicular velocity, which is h divided by 1.5. Now, let's look at swimmer 2's journey. Swimmer 2 starts at the same point A on the bottom bank, but swims perpendicular to the riverbank at 2.5 kilometers per hour relative to the water. Because of the current, swimmer 2 will drift downstream while crossing. They'll reach the middle of the river at point B, which is downstream from the target point M. After reaching point B, swimmer 2 needs to walk back upstream along the middle of the river to reach point M. The question asks at what walking speed this should be done to arrive at the same time as swimmer 1. Let's calculate how long it takes for swimmer 2 to complete their journey. First, the time for swimmer 2 to swim across to point B is the half width of the river, h, divided by their swimming speed, 2.5 kilometers per hour. During this swimming time, the current will cause swimmer 2 to drift downstream by a distance d. This distance equals the current speed times the swimming time. D equals 2.0 times h divided by 2.5, which simplifies to 0.8 times h. The time to walk back this distance at speed u is the distance divided by the speed. T walk equals 0.8 h divided by u. So the total time for swimmer 2 is the sum of the swimming time and the walking time. T2 equals h divided by 2.5 plus 0.8 h divided by u. Now, for both swimmers to reach point M at the same time, their total travel times must be equal. T1 equals T2. So, we have h divided by 1.5 equals h divided by 2.5 plus 0.8 h divided by u. Since h appears in all terms, we can divide through by h to simplify. 1 divided by 1.5 equals 1 divided by 2.5 plus 0.8 divided by u. Converting the fractions to decimals, 0.6667 equals 0.4 plus 0.8 divided by u. Subtracting 0.4 from both sides, 0.2667 equals 0.8 divided by u. Solving for u equals 0.8 divided by 0.2667, which gives us approximately 3.0 kilometers per hour. Therefore, swimmer 2 should walk at a speed of 3.0 kilometers per hour to arrive at point M at the same time as swimmer 1. Let's now visualize both swimmers' journeys with our solution. Here we can see swimmer 1 moving directly toward point M, while swimmer 2 first swims across and drifts to point B, then walks back at exactly 3 kilometers per hour along the middle of the river. When we use the correct walking speed, both swimmers arrive at point M at exactly the same time, confirming our solution.